Hello there, AP Physics 2. By request, finally, yes, finally. I mean, it's almost 2 weeks into this thing, and I'm now finally getting somebody to say, hey, could you help us with... Yeah, finally. There, I'm done with the guilt trip. So, let's look at a couple of these. Cylinders, equal cross-sectional area, contain different volumes of an ideal gas, sealed by pistons. There's a lot of moving pieces with thermodynamics. And the hard part is cutting through the stuff that doesn't matter. There's a weight sitting on top of each piston. The gas is the same in all four cases and is at the same temperature. The pistons are free to move without friction. Pressure. Okay, so the pressure, when you think about these pistons, is all about... approaching it not from PV equals nRT, but from pressure is force divided by area. I don't care what's going on inside of these things. The pressure is created by the weight and the area of this piston. It's going to move. The gas is going to allow the piston to move until it is in equilibrium, until the total downward force is equal to the total upward. In other words, the pressure caused by the piston and the pressure inside the gas is the same. So let's figure out this. Now, what you want to do at this point is, now that I've said that, you might want to pause the video and take this and run with it and see if you can figure it out, as opposed to just staring at me finishing the problem. That's my suggestion. Okay, so welcome back. Let's see if you did it right. So here I have a total weight. So for A, I have a total force, downward force of 12 newtons. Now, do they have the same area? Equal cross-section. Oh, divided by area. It's the same area for all of them. I don't even need to know what it is. So this one really boils down to whichever one has more weight is going to have more pressure. So A is 12 over, so this is going to also be 12 newtons over A. That's the pressure here for A, pressure for B. For C, it's going to be 4 newtons divided by the same area. And for D, it's going to be 20 newtons worth of weight, 20 newtons, divided by the same area, the cross-sectional area here. And that's the pressure by D. So this is why D is first, A and B are tied for second, and C is third. Now, let's see how they try to confuse us now. 22, equal cross-sectional area again, different volumes of an ideal gas. There's a weight sitting on very similar. The gas is the same temperature. Rank the mass of the gas in the cylinders. Okay. So this starts off the same. Different volumes of gas. So 5 liter PV nRT, same temperature. All right. So now we are going to need the volume, and we are going to, I think, go with the ideal gas law, because PV was nRT. All right, so it's the same gas but different volumes of it. So really, when they say rank the mass, we're really looking at N, which one has more gas in it. And we can figure out the pressure, or at least an indicator of the pressure for each, because they all have the same cross-sectional area, and they have different weights on top, different forces pushing down. So, but we can get a feel for that. Volumes are given. They're all at the same temperature. So this is the same and this is the same. So N is going to equal PV over RT. RT is just a constant for all, same constant for all of them. So I'm not really worried about that. Whichever one has the bigger combination of P times V wins. Now remember, so I write equals, and now I'm gonna say proportional to instead of equals, or I guess that's not proportional to. I think it's just here. That's approximate. Get my notation right. Proportional is just a single squiggly. So I can't say it's equal to because we're removing things. But remember, pressure, though, is going to be that force divided by area times the volume. But everybody's got the same area, same cross-sectional area. So really what this comes down to is force times volume. Whoever has the bigger force times volume has to have the bigger number of moles and therefore more mass. I'll let you, because it's the same gas, type of gas. All right, this guy. This one, this is a great physics question. I'm not going to lie. But it's frustrating because they give you so much stuff to chew on. You read this and you're like, I got the twice as many molecules and blah, blah, blah. Okay. Here's the thing. Regardless of whatever's going on, you put two things in opposite sides here, and this piston here is free to move. If the pressure here was more than, say, the pressure on the left, well, that would cause this piston to move to the left. Right? More pressure here is going to force it to move. But they tell you so it's free to move, and so it's going to move until it is going to move until the pressure here is the same as the pressure here, and then it's going to stop moving. If there is a pressure difference, it's going to move. So the pressure of the gas on the left side and the right, it's got to be equal. Otherwise, it would move. But I think they say in here, move without friction. Yeah, it doesn't matter. All right, so it's going to stop moving whenever it's going to find that sweet spot where the pressure is the same on both and stop moving. So most of it's garbage. The only way that thing comes to equilibrium is if the pressure is the same on both sides. Alright, so I'm not going to necessarily do all of them, but we'll say two cylinders are filled at the same height. Gases are different, and the cross-sectional areas of the cylinders are different. Both cylinders have pistons that are free to move. Temperature. Okay, so then temperatures. We probably are going to use PV equals nRT here. Maybe. Let's see. So, yeah. So let's do for A, well, in both cases, we'll do it this way. PV equals nRT. So they want the temperature, so that's going to be P times V divided by nR. The gases are different, but that doesn't really make a difference. N, I'm just looking to see if it, and the cross section, I'm not sure about N. Two cylinders are the same height H, and then the gases are different in the cross section. I'm going to assume this for now, that temperature, I'm going to assume the same number of moles. We may have to alter that as we go. So PV, so let's figure out this volume and pressure thing, shall we? So for A, the pressure for A is going to be 2 kilograms times 10, that's G, right, because that's your weight, divided by the area, and the area is just A. Whereas for situation B, the pressure is going to be, so we'll call this PA and we'll call this PB, is going to be, the total mass of this piston is 4 kilograms times G, which is 10, divided by 2A. What about the volume? Well, the volume in situation A is going to be, so the volume of a cylinder is, you can look at it as pi r squared times the height, but pi r squared is really just the area, cross-sectional area. So it's really the area of one of the sides times the height. So the volume of this one is going to be A times H, capital H, I guess. The volume for B is going to be 2A times H. All right. So I'm going to look at PV for each. Well, that would be 20 over A times A over H, so it's going to be 20H. This is going to be 40 over 2A, and it's going to cancel out these two. So this is going to be 40H. So PV for B is larger. And so I would say I'm a little skeptical. I'm not skeptical. I'm a little bit worried about number of moles. The type of gas won't make a difference. I'm gonna run with it here and say, all right, so that the temperature for B should be larger. I hope that's the answer I put down in my answers. I'm gonna go look. You just hate to have one of these be the wrong answer. All right. There we go. And this is number 24. 2. So I said that A is less than B. Yeah, okay, so I did get it right there as well. Okay, just making sure that I didn't contradict myself. 25. This is not one of the ones I think I gave an answer to. An insulated cylinder contains an ideal gas. The cylinder has a piston that is initially locked in place, When the pins are removed outward, say gone, the piston can move freely without friction. On top of the piston is an 8-kilogram metal disc. A student who is asked what will happen to the temperature of the gas after the piston is unlocked makes the following contention. The piston will move, but we don't know which way, whether it moves up or down. Since the cylinder is insulated, the temperature of the gas cannot change during the process. I don't like that part. I would agree that you don't know which way it's going to move. That part I'm all right with. And it's always, by the way, almost always the case in these things where let me get a little closer so you can see it better, but where there's some part of it that is right and some part that isn't. I agree you don't know. You don't know if the current pressure in this gas is enough to provide a force bigger than to move it up. But here's what I do know. Since the container is really insulated, it's hard for it to exchange heat, Q, right, with the outside surroundings. If the piston drops, it's going to drive the temperature of the gas up, and it's going to take some time for that heat to go to the atmosphere, to the surrounding environment. If the gas pushes this up, has enough pressure to do that, the gas will cool. And it's going to take a time for it to absorb energy back from the surrounding environment. So because it's insulated, I actually would say the temperature of the gas will change. Unless it's already in equilibrium. The only situation, if you remove them and it just stays there, then in that case I would say, all right, the temperature is not going to change. But the temperature can change, and it will go up if the piston drops, and it will go down if the piston is lifted up by the gas. I'm going to go all the way to 27, and then I think I've done enough of your work for you. Ideal gas, pistons free to move, pistons are at rest. All gases are at the same temperature. The diameter of the cylinder case B is twice as the others. And the mass of the piston is C. So pressure of the gases. This is, once again, this is pressure force divided by area situation. Keep in mind that doubling, so these all have the same area. This one, if we double the distance across, we actually make it 4 times the area. because the area would be the radius, right? So doubling the distance means double the radius. This radius is twice as big as this one. And area is pi r squared. So by doubling the radius, whoops, so area is pi r squared. By doubling the radius, you're going to quadruple the area. So this would be 4 times the area, cross-section area, as the other ones. 5. So this would be, the pressure here is 5 times 10, because that's the weight, divided by, we'll call it just area A. This, for example, is the same 5 times 10 for the force, but it's divided by 4A. This is 10 times 10, so that's 100, or 10 times 10, divided by A, and this is, this and this are the same. The position of the piston doesn't make any difference. So this is going to be 5 times 10 divided by A. So there's your winner. Then these two, and then this one's last. All right, hope that's enough help to get you started on some of those.